So we already looked at exponential functions, but now we're going to look at the opposite side of this, the inverse of exponential functions, which are logarithmic functions. So a logarithmic function is anything that looks like this. Y is equal to log base b of x. With a few exceptions, b is always going to be bigger than 0, so it'll always be positive, and also b is never going to be equal to 1. This will make a little more sense in a moment when we look at a few of these logarithmic problems. So the question is, what does this mean? What is a logarithm of b base x? Well, the easiest way to think of this is to think of it like this. Ask yourself a question. For example, to what power should I raise 3 to get 9? Okay, so what power should I raise 3 to get 9? Now obviously 3 squared is 9, right? So the power I should raise 3 to get 9 is 2. But I can express this using a logarithm. This is precisely what a logarithm means. A logarithm asks you what power you should raise something to get some other number. So for example, I could have written this as log base 3 of 9. This is the same thing as saying what power should you raise 3 to in order to get 9. So I could have thought of it like this. If I want to think of it algebraically, log base 3 of 9 is equal to something I don't know, some number x, right? Then I could actually go and rewrite this. This is the same thing as saying that 3 raised to some unknown power is equal to 9. So you can actually see there's a relationship between the logarithm and the exponential function. Anything that's a logarithmic function, I can go back and write it in an exponential form, and the opposite is also true. Anything that's in an exponential form, I can go back and write as a logarithm. So in this case, we know that this unknown x has to be 2, because 3 squared is equal to 9. So that means that x is equal to 2. So we can say that log base 3 of 9 is equal to 2. So we can do a few more simple ones like this. Something like this, log base 2 of 8. Well, this should be 3, right? 2 to the third power is 8. Or we can use this and solve it in a more algebraic way. Log base 2 of 8 is equal to some unknown x. That's the exact same thing as saying that 2 raised to the x power is equal to 9. What must that power be? Well, it must be a 3, right? So 2 cubed is equal to 8. So that means that log base 2 of 8 is actually equal to 3. Now we can take these and make them a little more complex. For example, what is log base 4 of 1/16? Well, in this case, again, I'll just set it up here as an equation. Log base 4 of 1/16 is equal to x. This is the same thing as saying 4 to the x power is equal to 1/16. But in this case, maybe it's still not quite so obvious. So in this case, I'm going to use a rule. I'm going to use a trick that we have. The trick is this, that for any of these, if we have a base equal to another base, so base raised to y is equal to that same base raised to x, if the bases are exactly the same, that's going to mean that the exponents have to be exactly the same also. Now, of course, we already said that b is not going to be equal to 0 and b is not going to be equal to 1. In fact, all of b's are going to be positive. So we don't have to worry about, if you think about 0 raised to any power, it's always 0. So obviously this rule doesn't apply then. Same thing with 1. When 1's raised to a power, it's always 1, so the rule doesn't apply here. So we've kind of already taken care of that with the stipulations that we have on our logarithms to start with. But we're going to use this basic idea. If I can write these two sides so they have the exact same base, then I can just set their exponents equal to each other. So in this case, I could actually rewrite 1/16 as 1 over 4 squared. And that I could just think of as 4 to the negative 2. So in this case, 4 to the x is equal to 4 to the negative 2. That means the exponents have to be equal to each other. And we that x is equal to negative 2. Okay? We could have seen this also, right? 4 to the negative 2. That will give you 1 over 4 squared, which is 1/16. So sometimes you get to where you can do more of these in your head. But for now, we'll say that using that rule, we can find out that log base 4 of 1/16, that's just equal to -2. What about this one, log base 3 of 1/3? Well, this is asking what power should we raise 3 to get 1/3, right? Or if we want to write an exponential function, 3 to the x is equal to 1/3. Well, I can rewrite 1/3 as a base of 3, right? 3 to the x is equal to 3 to the -1. In this case, I have two exactly equal bases, and then that means I can set the exponents equal to each other. X should have been -1 from the beginning, so the log base 3 of 1/3 is equal to -1. Again, the more of these you do, the quicker you'll be able to just do them in your head and figure that out. But again, the logarithms are not a difficult thing to understand, and they look a lot more complicated than they actually are. We're just trying to ask, what power should I raise this base to in order to get this number here? So let's look at a special base that we use. We already talked about the number e. Log base e has a special shorthand. This is called the natural log. And we use this quite a bit, so it actually has a shorthand. So instead of the log base e, we write this as ln. It comes from the French way of saying natural log. So instead of, for example, log base e of x, it's typically just written ln of x. So that just means the log base e of x. So you'll see this one quite a bit. Don't get confused. It's just you treat it the same way you treat any other logarithm. It's just that it has a special base, the number e that we've talked about a little earlier in the lecture. Okay, so let's look at a few more properties of these logarithms. What about log base 5 of 1? Well, this is saying what power should you raise 5 to in order to get 1? Well, if you're going to raise 5 to a power and get 1, the only time that'll actually happen is if you raise it to the 0th power. Any other power, you'll never get 1, right? So in this case, log base 5 of 1 is equal to 0. Okay, what about log base 3 of 1? Well, again, you run into the same thing, right? If you raise 3 to some power and you're going to get 1, the only power you can raise it to is 0. So log base 3 of 1 is also equal to 0. What about natural log of 1? Well, again, same thing. This is the same thing as saying log base e of 1. So what power should you raise e to get 1? Well, e is just 2.71 approximately. So you should raise it to the 0th power to get 1. This means the natural log of 1 is also 0. So this brings us to an interesting rule. Any base of 1 is always going to get you 0, no matter what the base is that you're going after. So this is one of the rules we're going to mark down. All right, so let's look at some other examples. Log base 4 of 4. Think about this one. You have to raise 4 to a power to get 4. You better raise it to the first power, right? 4 to the first power is equal to 4. So that's going to be 1. Log base 2 of 2, again, the same thing. 2 to the first power is equal to 1. I'm sorry, 2 to the first power is equal to 2. So log base 2 of 2 is equal to 1. What about natural log? You can kind of see where I'm going with this. Natural log of e. Well, this is the same thing as saying log base e of e. So e raised to what power is equal to e? Well, in this case, e raised to the first power is equal to e. So natural log of e better be equal to 1. So you're noticing a pattern here. This means that if we take log base b of itself, you'll always end up getting 1, and that should make sense as well. So b to the first power, you always get b back. Okay. Let's look at a few more. What if I asked you log base 5 of 0? Well, if if you try to raise a positive number, we said all of these little bases are going to be a positive number, right? If you try to raise a positive number to any power, you'll never get 0. Okay, right? I'm thinking about what base I'm raising 5 to get 0. It's impossible. And in fact, if I think about this as 5 raised to some power is equal to y, as in my graph that we were looking at earlier, we know the graph looks like this. Well, is there any x value that will give you a y value of 0? Well, no, because there's an asymptote right here where all the y values are 0. There's no x values that make that cross the asymptote. So in fact, there's no number that works for this. There's no number you can raise 5 to get 0. So we're going to say this is actually undefined. So any log of 0 is always going to be undefined. Okay? Because it just doesn't make sense. So even if you don't memorize the rule, when you get to it, you won't be able to figure out what that number is. But this is definitely a good one to keep in mind. What about the natural log of -4? Or if you prefer, log base e of -4. This is saying that e raised to some power is equal to -4. But we know that e is a positive number, right? In fact, all of our bases are going to be positive numbers. You can never raise a positive number to any power and get a negative number. It will never happen. So again, this is going to be an undefined logarithm. Okay, what about log base 3 of -1? Well, again, you run into the same problem. What power can you raise 3 to get -1? Well, if 3 is a positive number, you'll never raise it to any power and get a -1. Even if you raise it to negative powers, you'll just get fractions, right? Like 3 to the -2 is just 1 over 3 squared, or 1/9. So that doesn't help us at all. So in fact, this is undefined as well. So we're going to say that the log base b of any negative number, this is also going to be undefined. Okay. And if you actually look at the graph of what a logarithmic function looks like, and we're not going to do too much graphing with this, or really any graphing, but if you actually look at the picture of the graph, you'll kind of see why this is true. The graph, for example, y equals log base 2 of x, it looks like this. And you'll notice that on the graph, there's no negative x values. Okay? So there's no negative x values on the graph. It's not in the domain of the graph. So you can never take the log of a negative value because this x is right here. It can't be a negative value. There's no y's corresponding to it where you get x is negative value. So if you take a look at the chart, it becomes really obvious to look at the graph. But also, you don't have to know the graph to realize that. You can just actually try to work it out, and you'll see that the numbers don't quite work.